Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
1877 Ludwig Boltzmann on the relationship between the second law of thermodynamics and probability calculus. The year 1877 marks a crucial juncture in the history of physics, a pivotal moment wherein Ludwig Boltzmann, a man of prodigious intellect wrestling with the fundamental laws governing the universe, presented his groundbreaking work on the relationship between the second law of thermodynamics and probability calculus. This essay endeavours to embark on a critical and comprehensive evaluation of Boltzmann's seminal paper, dissecting its core claims, meticulously analysing their internal coherence, and understanding their lasting influence on the scientific landscape. We shall navigate the intricacies of his arguments, unearthing the conceptual frameworks he employed, and scrutinising the evidence he marshalled in support of his revolutionary ideas. Our primary focus remains firmly anchored on the work itself, tracing the contours of Boltzmann's thinking with the precision of a laser, acknowledging the intellectual context only as it illuminates the intricate mechanics of his reasoning. Section 1 Introduction and the problem of entropy. Boltzmann's paper commenced with an explicit acknowledgement of the prevailing problem of entropy. He noted the established, yet somewhat mysterious, increase of entropy, a measure of disorder within a closed system, as delineated by the second law of thermodynamics, a law that stands in stark contrast to the time-symmetric nature of the fundamental microscopic laws of physics. What exactly determines the inexorable march toward equilibrium, a state of maximum entropy wherein energy is distributed randomly throughout the system, seemed, to many within the scientific community, a deep philosophical quandary. Boltzmann recognised that the challenge lies in reconciling the irreversible nature of thermodynamic processes, as manifested in the second law, with the time-reversible nature of the underlying mechanical laws governing molecular motion. He explicitly stated the objective of the paper to illuminate the relationship between the second law of thermodynamics and probability calculus, a pursuit that, at this point in time, looked like an audacious undertaking. He aimed to provide a mechanical explanation for the second law, to understand it, not as a rigid, inviolable commandment, but as a probable outcome of statistical behaviour, an average property of a system composed of a vast number of particles. This, in itself, was a radical departure from the more traditional, deterministic approach prevalent within the field. Boltzmann's introduction laid the groundwork for his subsequent argument, framing the second law in terms of the most likely state of a system, implying a probabilistic interpretation that would form a cornerstone of his entire analysis. Section 2. The concept of the W function and its connection to probability. The heart of Boltzmann's argument resided in his introduction of the W function, which he utilized to link entropy with the probability of a system being in a specific state. This function, subsequently denoted as S equals K times the natural logarithm of W, written out explicitly, established a direct connection between the thermodynamic entropy, represented by S, and the probability, W, of a given macroscopic state. The proportionality constant, later elucidated, would become Boltzmann's constant, K. The W function, in this context, was not simply a measure of the state itself, but a reflection of the number of microscopic configurations, the possible specific arrangements of molecules that are compatible with the observed macroscopic properties of the system, such as its temperature and pressure. A high value of W represented a greater number of accessible microscopic states and indicated a higher probability. For the observed macroscopic state it therefore suggested greater entropy. Boltzmann recognised that macroscopic states with higher entropy are, in this framework, the states that are more probable. He was, in essence, claiming that the second law of thermodynamics is fundamentally a statement about the likelihood of various states, an understanding that overturned the traditional conception of the second law as an absolute and deterministic law. The argument here pivots upon the idea that systems tend towards the most probable state at entropy increases precisely because there are far more microstates associated with higher entropy macros. Section 3 application to a simple model gas in a box. To illustrate his concepts, Boltzmann presented a simplified, yet illuminating, model: a gas confined within a box divided into equal compartments. He posited that the probability of all the gas molecules being concentrated in one half of the box, for instance, is dramatically less than the probability of the gas being evenly distributed throughout the entire box. The even distribution represents a state of greater disorder, corresponding to a higher entropy and, crucially, a higher value of W. The uneven distribution, on the other hand, represents a state of lower entropy and much smaller probability. Boltzmann used this model to show how the second law emerges naturally from the statistical behavior of molecules. He emphasized that although it is theoretically possible for the gas to spontaneously concentrate in one half of the box, the overwhelming likelihood, as the number of molecules increases, is that the gas will spread out evenly. The model highlights the probabilistic nature of the second law. It does not forbid the decrease of entropy in a specific instance, but it makes it incredibly unlikely. The power of this section comes from its simplicity, illustrating the fundamental principles with a minimum of mathematical complexity. The model successfully conveys the core probabilistic argument, paving the way for a more rigorous mathematical treatment. Section 4. The derivation of the Maxwell-Boltzmann distribution. A critical element of Boltzmann's work was his derivation of the Maxwell-Boltzmann distribution, which specifies the distribution of molecular speeds in a gas at a given temperature. This distribution is not merely a descriptive result, it's a cornerstone of Boltzmann's argument. It provided a concrete connection between the kinetic energy of the gas molecules and the macroscopic properties of the gas, such as its temperature and pressure. Boltzmann demonstrated that, starting from the principles of statistical mechanics and probability, the most probable distribution of molecular speeds is a distribution that follows the bell-shaped curve, the familiar shape we now recognize as the Maxwell-Boltzmann distribution. The derivation, while complex, showcased his sophisticated use of mathematical techniques, including calculus and probability theory, to solve the problem. The Maxwell-Boltzmann distribution offered a powerful method of verification. It allowed him to make specific predictions about the behavior of gases, which could be empirically confirmed. This section thereby served to underpin his probabilistic interpretation of entropy, linking it to the measurable properties of the gas system. In this derivation, he explicitly integrated the concept of probability into the analysis of molecular motion, solidifying the connection between microscopic and macroscopic properties. Section 5. The concept of statistical fluctuations. Boltzmann, aware of the potentially counterintuitive implications of his probabilistic interpretation, directly addressed the possibility of statistical fluctuations. These fluctuations, which represent temporary deviations from the most probable state, such as the spontaneous concentration of gas molecules in one half of the box, were not dismissed but explicitly acknowledged. He predicted that, over sufficiently long periods, such fluctuations would occur, but they are exceedingly rare, particularly as the number of molecules increases. He recognized that the second law of thermodynamics is not a universal decree that the entropy of a system can never decrease. It is a statement about what is most probable. The implication is that a system may, from time to time, spontaneously decrease its entropy, although this is always temporary and exceptionally unlikely, particularly for macroscopic systems containing a considerable number of molecules. Boltzmann's acceptance of these fluctuations represents a crucial element of his theory, allowing the model to withstand the criticism of absolute determinism, and also suggesting that the second law has a statistical basis. The acknowledgement of fluctuations distinguished Boltzmann's work and provided a crucial tool for explaining phenomena like Brownian motion, where the movement of particles becomes more visible and appreciable. This added crucial nuance to his hypothesis, highlighting the probabilistic nature of the law, not its absolute inviolability. Section 6. The application to chemical reactions and equilibrium. Boltzmann extended his analysis of the second law to the domain of chemical reactions, exploring how his probabilistic approach could explain the concept of chemical equilibrium. He argued that chemical reactions proceed in the direction that leads to an increase in the total entropy of the system. At equilibrium, the total entropy, the overall measure of disorder, reaches a maximum. This maximum corresponds to the state where the rate of the forward reaction equals the rate of the reverse reaction. Chemical equilibrium, therefore, does not represent a static state but rather a dynamic balance where the rates are equal. This interpretation of chemical reactions, as states driven by statistical probability, offered an elegant explanation for the equilibrium constant and how it relates to the thermodynamics of a reaction. Boltzmann, in this section, demonstrated that the fundamental laws of thermodynamics and the second law are, in fact, essential for understanding the behavior of chemical systems, again emphasizing the broad applicability of his probabilistic approach, making it attractive to chemists. Boltzmann's work provided a theoretical framework to understand and predict the outcomes of chemical reactions, linking them to the underlying dynamics of molecular interactions. Section 7, addressing objections and counter-arguments. Boltzmann, anticipating the criticism his work would face, directly addressed several objections and counter-arguments. A principal concern centered on the seemingly irreversible nature of the second law, given the time-reversible nature of the underlying microscopic laws of physics. His response centered on the statistical nature of the second law. He emphasized that the second law is not a deterministic law, like Newton's laws of motion instead. It's a statistical law, meaning that the observed behavior of systems is the most probable behavior. The law does not prohibit time-reversed processes, it merely makes them exceedingly unlikely. Furthermore, Boltzmann skillfully addressed the issue of Loschmidt's paradox, an apparent contradiction that had surfaced. The paradox posited that if microscopic interactions are time-reversible, then, from this viewpoint, time symmetry should exist at the macroscopic level. Boltzmann was able to argue that by considering a vast number of particles, he could show how any time-reversed scenario would be significantly improbable, effectively resolving the paradox. Boltzmann's willingness to tackle these objections demonstrated the robustness of his theory and his willingness to engage with the scientific community on fundamental issues. He demonstrated that the second law, as a probable outcome of statistical behavior consistent with the time reversibility of the underlying microscopic. Section 8. The connection to Clausius' formulation of entropy. Boltzmann's work reinforced the ideas of Rudolf Clausius, who had been instrumental in formulating the concept of entropy. Clausius previously defined entropy as the measure of the energy unavailable for work. Boltzmann's work provides a theoretical basis for this definition, explaining entropy in the context of the number of possible microstates associated with a given macroscopic state. By linking the entropy to the probability of the system, Boltzmann clarified the underlying mechanical basis of Clausius' formulation. The connection provided a deeper and more profound understanding of entropy. It allowed scientists to see the link between the abstract thermodynamic concept and the concrete behavior of molecules. In this context, entropy is not just a mathematical quantity, it is a physical property of the system, reflecting the degree of disorder and randomness at the molecular level. This connection was significant, and it helped consolidate the acceptance of Boltzmann's ideas, as he was not necessarily overturning the accepted scientific principles. Section 9. Implications and predictions of Boltzmann's theory. The implications of Boltzmann's work far exceeded the immediate realm of thermodynamics. The paper suggested that the universe could be a self-organized system. The concept also had substantial repercussions for the interpretation of the arrow of time. Boltzmann's work provided a powerful theoretical framework for understanding many physical phenomena. The principle of entropy was seen to have the potential to be applied across disciplines. One of the most significant predictions was the behavior of Brownian motion. Boltzmann's work provided the theoretical foundation that later allowed scientists like Einstein to successfully predict and interpret Brownian motion, thereby providing solid empirical evidence of the existence of atoms and molecules. This helped legitimize the concept that the second law is, at its heart, a statistical rule, and not an absolute one. Boltzmann's work, therefore, paved the way for the development of statistical mechanics as a distinct discipline. Section 10 Critiques and subsequent revisions. Boltzmann's work, while groundbreaking, was not without its critics, and was not immediately accepted by the scientific community. One of the most vocal critics was Ernst Mach, who objected to the use of atoms and molecules as theoretical entities, viewing them as metaphysical speculations beyond the scope of scientific inquiry. Mach favoured a more empirical approach to the study of physics. Opposition stemmed from the apparent contradictions between theoretical models and observations. The concept of statistical fluctuations, although a crucial element of Boltzmann's theory, appeared to run counter to the second law itself. Early on, criticism was rooted in the assumption that the second law was absolute and any perceived deviations from it, such as fluctuations, represented a failure of the theory. Boltzmann was able to defend his theory, and subsequent work, including the studies of Brownian motion, largely resolved these objections. Boltzmann's work underwent revisions, largely reflecting the scientific community's acceptance of the atomic concept. It was the acceptance of atoms into the scientific paradigm that allowed Boltzmann's paper to finally gain widespread acceptance. The revisions, notably, did not fundamentally alter the core claims of the paper, but rather refined the mathematical tools used to express them and address criticisms. Conclusion: Ludwig Boltzmann's 1877 paper on the relationship between the second law of thermodynamics and probability calculus represents a watershed moment in the history of physics. His work was significant. It established a profound and durable connection between the second law of thermodynamics and the concept of statistical probability, thereby providing a mechanical explanation for the behavior of entropy. Boltzmann transformed entropy from a concept to a measure through the introduction of the W function and the application to a variety of systems, ranging from gases in boxes to chemical reactions. He demonstrated that the second law is a statistical, rather than absolute, law. The work illuminated the microscopic underpinnings of macroscopic thermodynamic properties. Although confronted with both vigorous skepticism and resistance, Boltzmann's insights ultimately reshaped our understanding of the universe. He resolved the apparent conflict between the second law's irreversibility and the time reversibility of the microscopic laws, are recognizing the probabilistic nature of the second law. His work, in its acknowledgement of statistical fluctuations, not only underscored the probabilistic nature of the law but also provided a path toward understanding various physical phenomena, the derivation of the Maxwell-Boltzmann distribution, the connection to the framework articulated by Clausius, and the explanation of chemical equilibrium all served to underscore the broad applicability of his statistical mechanics. While the paper faced criticisms and required some subsequent revisions, it provided an enduring framework, setting the stage for significant scientific work. Today, Boltzmann's work continues to inspire and inform, confirming its stature as a landmark achievement in the history of science. It offers a powerful testament to the transformative power of probabilistic reasoning and understanding the mysteries that form the fabric of the universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.